You know, Christmas isn't far away, and if anyone wanted to get their teacher a present, ah, what is this? This is physics, isn't it? Sorry. What lesson are we on? What did we do last time? Cool. See, I actually feel like perhaps the power's broken on the laptop because the battery's not charging up. It's stuck at 6%. It keeps flashing here. You know, so maybe I need to get a new battery. Maybe that will fix everything. I suppose we should wait for Kim. It would be the only decent thing to do. Since I did ask her to get her laptop. Is she in the other building? Laptop. Did anybody have Thanksgiving yesterday? Thanksgiving yesterday? Nobody had a special meal? That's not really Thanksgiving food. My wife's American, you see, so we had Thanksgiving. Turkey and pie.
Oh, really?
I had 3 pieces of pie.
I had pie ice cream.
Good. I had a pumpkin pie, an apple pie, and a chocolate pie. Delicious. So good. So good. Kim will be so pleased to see that the laptop's working. Kim, great news! It's working! But, thank you, because if it breaks, we can use your laptop. You're a very kind student, thank you. Okay, so now we'll start at Kim's back. Resistivity. And this lesson isn't so difficult. It just continues with what we did last time, which was resistance. Okay, you got that? Yeah. Alright. It's only actually 2 things to have a look at. All electrical devices, bulbs, TVs, PCs, phones, they have some resistance. We were talking about this last time. What's the unit for resistance? Ohms, yeah. A resistor is an electrical device that gives some amount of resistance. It's used in experiments and circuits. And normally the work done is heat. So small resistors are really just small heaters. Here's an example of one. So you have these little things called resistors, and all they do is, it's like they make it harder for the current to move through it. Now you might say, why would you want to do that? Like, wouldn't you want the current to move easily? A few reasons. One example is, perhaps you have some laptop and you don't want the current to be too big, so you have a resistor, you know. Or, as we'll see later, you can actually do things with resistors, like that lets you change the voltage. Because remember what we said, what a resistor does, it takes some of the voltage out of the charge. So remember, I think we said 1 ohm means that 1 volt is lost, right? So you actually may want to drop the voltage. Can you think of some device that you might have that needs a low voltage? So, like, I think your phone. I think if you have your plug, does anyone have their plug for their phone? No? You have yours?
Yeah.
I think I'm going to guess, if you want to check, I'm going to guess it says 6 volts for your phone. We'll see now. Now, I don't know, I don't think I told you this, but you might know this from your home country. What voltage is provided by the power supply here in the home in Ireland?
230.
Yeah, it's between 220 and 240. What is it back in China?
120?
Yeah, 120, okay.
220.
Your relation?
No idea.
No idea. 5.25?
5.2.
5.2, okay, so nearly 6 then. No idea. No idea? What's it in Korea? 220.
220.
Not 120?
220.
Are you sure? No, because in some places it's 120. US is this. What's it in
220.
Sudan, huh?
220.
220 as well, okay. And are these 3 pins? Nobody has 2 pins.
2 pins and 3 pins.
Yeah, both.
Yeah.
Yeah, okay. So resistors can be used to drop resistance because I promise you, you can test it out. If you put 220 in a phone and it needs 5.5, the phone will explode, okay? So resistors are useful this way. The work that they do is that they get hot. They get a little warm. So let's think about what might, in this resistor here, it's just a little, it's like a little insulator nearly. The current has difficulty passing through it. What might affect it? So if we look at this picture, what might affect the level of resistance? So let's have a look. Do you think the length would affect the resistance? If it was longer, would that affect it? Would there be more or less? What do you think? Yeah, I think so too. Right, okay. What about the diameter? That would affect it. Yeah, okay, it does. Yeah. Well, the type of material? Yeah, of course, that would affect it. So you can actually put these all together and you can get a formula to calculate. Now, before you write the formula down, I'll just explain it. If you want to know what the resistance is, you need to know 3 things about the resistor. 3 things about the resistor. You need to know how long the resistor is. You need to know the area of the face. And you need to know this constant, which is different for each material. So, if you're talking about insulator, do you think this constant here will be bigger or smaller? Look at how it enters the formula. Insulators, do they have bigger or smaller resistance? What do you think? Bigger resistance. So what do you think the constant here? It'd be bigger for materials. Now what's interesting is the area. If the area is bigger, it actually makes the resistance smaller. So if you have a bigger area, it actually lets the current pass through more easily. Okay. L is the length, A is the area, and rho is a constant. And we'll talk about that constant in a moment. So you can write this formula down, and just write down what each letter represents. Chocolate biscuits, Siva? Cookies, nice. You're continuing your Thanksgiving celebration into Black Friday, huh? What are you doing in maths class at the moment? Second derivative. Do you have maths today? No. No, okay. Okay, continue. You got that, Kim? Yep. Right. That constant has a name. Firstly, it's a Greek letter. So which Greek letter is it? What's that Greek letter called?
Rho.
Correct, rho. Now that's the problem in maths and physics is sometimes you have to reuse letters. We've already used rho before. Where did we use it before? density, so we have to reuse it. But of course, context. If we're in an electricity question and we have the symbol rho, we can't be talking about density. But if we're in a material question, then we're probably talking about density. It only becomes confusing if we mix the two chapters together. Okay. That constant is called resistivity. And it's a measure of how much an electrical conductor stops the flow of electricity through it. Now, you just need the first sentence. But I should tell you, in the exam, for the definition, they want the first sentence, but then they want you to do this. They want you to say, resistivity is RA over L. I don't really like that they want you to do this. So you can actually see a definition of resistivity. It's like 1 ohm by 1 meter squared per 1 meter. But like, what the heck does that mean? You know, like, it's not exactly. It doesn't exactly have a natural understanding. That's why I prefer this definition, but they don't like it in the exam. So you would need this sentence together with this formula. Okay. So just the first sentence here is enough. And you all figured out correctly, well done, that most metals have a low resistivity because it's a conductor. And most insulators would have a high resistivity. The units. Now, let's just work out the units before we continue. So if I have this formula, what's the units for OR? Ohms. A and L. So what's the units for resistivity? It's ohm meters. The units are ohm meter, written like that, and that measures how much resistivity there is in ohm meters. Oops, sorry. Okie dokie. Got that? Continue, guys? Yeah? Yeah? Okay.
And the formula.
This here, yeah? How many cookies do you have there?
I know, I had one.
Oh, just one? That's good. Because aren't they like on special offer? You can get like 2 of them. Like you get a discount or something. In Subway, yeah?
Yeah.
Yeah. A good healthy breakfast to start the day. Any coffee drink? No? I don't think I usually see you drink coffee.
Not that much.
No. I had a student from Sudan last year, and he said there's a biscuit that you dip into your coffee or tea, and you mix it in until it melts. Is that? Yeah.
Some people do that,
Yeah. That sounds terrible to me.
yeah. It's terrible.
Yeah.
It looks terrible.
Yeah, because I feel like I don't like the feeling of the biscuit bits in the tea. It's like, ugh, not pleasant. Not pleasant. Okay. And I had a student from South Korea last year who also had to go to the doctor because of her eye. So we were wondering if when South Korean students moved to Ireland, they developed this problem.
What was her name?
What was her name? Japers, I've forgotten now. Yeah, no, sorry, I forgot. And I suppose you should find this out now. Next year I will forget all your names too. I'm sorry. I'm sorry, that's life. Chrissy, that was it. Yeah, okay. All right. So an insulator. What would you give as a definition of an insulator? If you think of, you know this word from chemistry, I think. So what would you might say an insulator is if we were talking about electricity? What definition might you give?
No free electrons.
Yeah, you don't even have to make it as fancy as that. You could just talk about the resistance. So if you were, yeah, you could kind of say it's high resistance, couldn't you? Which amounts to saying not really many free electrons. So an insulator will offer an appreciable level of resistance and will often have a high level of resistivity. I'm not so strict about this definition because Matt just gave a perfectly fine definition from chemistry class. An insulator doesn't have many free electrons. You could probably imagine other definitions too. Yeah? Got that? So you can kind of guess what's going to be a conductor.
Low level of resistance.
Yeah, that's it. A conductor will not offer an appreciable level of resistance and will often have a low level of resistivity. Copy, paste. Yeah. You got that, yeah? Yeah. A couple of people write and then we'll continue. So how do you talk much about this in chemistry? Just one class, was it, or like you knew this from chemistry? So okay, but has Lorraine talked about it?
Yeah, but not much.
Yeah, mentioned it, yeah. Has she talked about like examples of different materials that are conductors and insulators? Like what would be insulators? Plastic, yeah. Huh? Yes, yeah. Anything else? What about water? It's kind of 50-50 now.
With iron,
That's it. Oh,
Polar.
it distilled water, not contaminated with any salts. That is it's kind of an insulator. But when you have water that's mixed with salt and fluoride and other things, like tap water, is tap water an insulator or a conductor? It's a conductor. But the water that you can buy from the pharmacy, the distilled water, that's an insulator, or at least it's a very bad conductor. The reason you can't mix a water and electricity at home, water and electricity is quite a bad mixture at home, is because the water comes from the tap, and the tap water has, contaminants in it that make it a conductor. Yeah. But pure water by itself is a very bad conductor. Very bad conductor. Okay. So, let's have a look at some values, okay? Graphite. Graphite is actually an excellent conductor. So the graphite in your pencil is a very, very good conductor. Did you know that, or is that, you knew that, yeah? What I sometimes do in class, I draw with a pencil on a piece of paper, and I'm actually able to pass a current through the pencil mark on the paper. You can actually do this. If you take a pencil and just scribble a line on it, you can actually get a current running across the top of the paper. Okay, the next material is copper. Copper is obviously an excellent conductor. Not as good as graphite, is it? Because, I mean to say, better than graphite because it's a smaller value. Now, this is interesting. If copper, copper, yeah. Copper is a better conductor than graphite. Graphite is still very good though. But we don't use graphite, even though it's still a good conductor. We use copper. Copper has one advantage over graphite in that it's more flexible. Because remember when we were doing Young's modulus, we said the Young's modulus is very small for the graphite. It's very rigid, it's easy to break. The copper is a bit more flexible, you can kind of change the shape. So you can't really have graphite wires, but you can have copper wires. Okay. Nickel. Nickel is nearly as good as copper. It's still a good conductor. Okay, next material. Nichrome. Nickel and chromium. It's not as good as copper and nickel, but it has one advantage over copper, and that is that it is cheaper than copper. I think a lot of coins maybe might have some of this in it. No country uses copper anymore in its coins. They used to, but it's now too expensive. Now on to the insulators. Now I want you to notice how big the value change has been. We have gone from 10 to the minus 6 to 10 to the plus 14. So that's clearly an insulator. There's a lot of resistance in these materials. But you knew wood was an insulator. Right, the next one. Rubber. Like in a car tire, something like this.
Isn't the steel conduct electricity with
Which material?
like wood?
Everything can conduct electricity if the voltage is big enough. True. The question really is how friendly the material is to the current. So like if you had even a piece of wood, a current will pass through it. Like think about a bolt of lightning. Bolt of lightning hits a tree, and the current runs through the tree and hits the ground. So insulator doesn't mean it prevents the current. It just means that it offers a huge resistance to the current. Yeah. All okay?
No, it's
Huh?
just thinking with something inside that.
Oh, okay. Right. You can actually, but just to point out, you can make a resistor out of a conductor and vice versa. This is what I was just talking to Matt about. So, although wood is an insulator, if you put enough current through it, you can have it conduct electricity. And the same goes for a conductor. You can make it an insulator. Now, how can you do that? So if you look back at this formula, imagine I want to make this big, but I can't change this because maybe I'm using copper. If I want to make this big, I could do two things. I could either make this big or this small. In fact, if you make this small enough, you can change the copper into kind of like an insulator where the current has a difficult time passing through it. Okay, so you cannot actually switch between the two. It's quite common to use nichrome as an insulator. If you use a fine enough piece of nichrome, you can actually make it become an insulator and it will become hot when a current passes through it. Okay. Let's have a look here. Here's a good example. The nichrome is being used to make an electric heater. Does anybody have an electric heater at home? Have you ever looked inside of it? If you look inside of it, it actually looks very, very simple. You have a metal box, right? And on the top of it you have these holes, yeah? Lots of holes in them. And have you ever looked inside of it? What do you remember, if you can, of what? Yeah, it looks like lots of like little cylinders running around like this, yeah? This is actually just nichrome wire. All this heater is doing, oh, and there's usually a hole at the bottom as well. All this heater is doing is passing a current through nichrome wire. And this wire has a high resistance. So what happens is it produces heat. And the heat comes out the vent out on the top. And there's usually a hole at the bottom so the cold air gets pulled up. This is why electric heaters are so cheap. You know, like if you went to Argos, you could probably get something like this for like 25 euros. The reason it's so cheap is all it is a box with a wire. You know, it's like a light bulb. All a light bulb is a glass box and a wire. It's not exactly advanced technology. So you have an electric heater made of nichrome wire. The nichrome is 20 centimeters long. Now that's not really realistic. I think in a real heater it's more like a meter long. It's 5 millimeters in diameter. I want you to calculate the resistance. So I want you to use this formula. We know this from our table. We know this, and the area, you can imagine it as a circle. Okay? I'll give you a minute to calculate this. I don't think it should cause you any problems. And then I'll do the answer now in a minute. Let me open up my calculator. Oops, sorry. It's gotten very cloudy, hasn't it? It was nicer this morning. Right, do we have answers? Yep.
2.85 into the power negative.
I think I should change these numbers. I think I should make them bigger. Anyways. Oh, Kim, you use such bad language. Have we got answers? Siba, do you have an answer?
I don't have the formula.
Huh? You didn't write it down?
That's one thing. You have to find the cross-sectional area.
Yeah. It's not a big deal, right? Guys, this is taking longer than I would have thought it should take. I know a couple of people have answers. Do you have an answer?
It's 4.4.
No. No, I think I know why. You got 2.2, didn't you?
2.8.
Yeah. The diameter, perhaps. What's the radius? 2.5, yeah. Yeah.
How many meters?
2.5 and
Meters. Right. Right, look. Guys, what's the rho? What's the resistivity for nichrome? 1.1 times 10 power minus 6 times, okay, what's the length? 0.2. And the area is pi or squared. Now what's the radius? 2.5 millimeters. Milli is 10 to what power? Minus 3. So the answer is that, which I don't think anybody got. Congratulations. 0.011 ohms. What the heck happened, folks? What happened? So, Matt, what went wrong for you?
the radius. I
Yeah,
used 0.005. But to reset that, I forgot.
You converted to meters, but you forgot to divide by 2. Okay. What happened to you, Matt, or George?
Just left it 5. I left.
You left it at 5?
Can you show me the full?
The calculator?
Yeah.
It's like this.
Yeah.
Kim, what was your mistake?
Diameter?
As well, yeah. Siba?
No, I was doing it.
Oh, you were in the middle of doing it, okay. Continue, folks. Is this okay? I hope this is okay. This is
So y is 2.5 times 10 minus 3.
yeah, instead of what? Instead of 5?
Why is this one?
Yeah, because look, you have a circle. That's diameter, that's radius. You know? D4. So this here, this is the diameter. The radius, the or, is half of this. 2.5. Yeah? Is that okay, Chow? You know what I'm saying? You don't look like you know what I'm saying.
No.
Okay, thank you. Circle, right? What's this called? Now don't say it, anybody. Chow, what's this called?
Diameter.
Good. And what's this called?
Radius.
Good. Radius, diameter.
Yeah.
The diameter is 5.
So
Yes?
radian is 2.5.
Yes. Correct.
And yeah.
Millimeters.
Oh.
mm
is
Mhm.
okay.
Yeah.
Yeah,
Got it?
got it.
Got it.
Finish that one.
Yeah, go ahead. Is this okay?
Yeah.
Is it okay? Because I just used one formula, so are you sure it's okay? Okay.
It's just not as easy as I thought. It's easy, but it's not easy.
No, it is easy. Yeah, no, I would say it's easy. Okay, well look, we'll have a tutorial in a minute. We'll have a look at the questions you want me to do. How many questions did I give you on this one today? How many have you got today for this one? There's only 4, is it?
4.
They're all very short. So, why don't you do those until 12 o'clock, and then we'll have tutorial at 12 o'clock, and we'll do whatever questions you want. Do we need to do questions from materials? Probably. Do we? Yeah, I have. Yeah. I kind of feel like we might have to go as far back as page 59, maybe. Anyways, if you can try these questions for a few minutes.
Oh, this
Yeah.
is a formula book.
Yeah. The last few pages of the formula book. You've not noticed this? But there's a...
No, we're almost done with the book. Huh? 13 pages left after